So good morning, everyone, to the defense of Frank Luan. Again, I apologize for not being able to be in person there. So Frank joined us as a programming language student when he started here. And one thing about Frank, which this suggests, is that amazing research breadth. Actually, at Facebook, I think that was in 2017, 18, he was applying machine learning to code development so long before it was very fashionable. I think that was the time when he's using neural networks for search, code search, and things like that. And then, like I mentioned, he came here as a programming language student. I actually remember when I interviewed him. I'm not sure if you remember, Frank, when I called you. Um, and because he was about to fall through the cracks because it's programming languages, systems, and things like that. So he joined us, and today he's going to talk about how to redesign and to optimize large-scale data processing for the new kind of data, multimodal data. But in between, he has done other work. He has worked on SkyPilot. He has worked on neurocards, on cardinality estimation, and he has worked on BALSA, which was using reinforcement learning for query optimization. So again, as you can see, fantastic breadth of work. You are going to today only to hear about the tip of the iceberg. In addition, I think Frank, despite all of this work, has been a pleasure to work with Frank. He's very always calm, unassuming, not flashy, but under all of this, whatever he's doing is core, is fundamental, is solid, right? Is steady. So again, Frank, has been a pleasure, and I am very much looking forward to your presentation. So please take it from here.
Okay. Thank you very much, Jan. And yes, I remembered all the way from the interview. I think I started at Berkeley with a background in machine learning for coding, but then I sort of drifted to systems, and then here we are. But yeah, welcome everyone to my talk. And then for people online, I'm very happy that you guys can join us. There are people from I know from all the way from middle school. So I'll leave that sort of acknowledgement and thanks for later. But let's get through this technical content in maybe half an hour, and then we can talk about other stuff that Yang mentioned before. Right. So, all right. So the topic of today's dissertation is an extensible architecture for distributed heterogeneous processing. So the general plan for today is that okay. Oh. I think that's right. So the plan for today is I will talk about what the distributed heterogeneous processing is. I will talk about two work that I've done in this realm. So one is called Exoshuffle with people are in this room. And the other one is a streaming batch model. And then it became later Ray data and with a lot of people from AnyScale. And then we'll see some future directions. So let's start with the case for distributed heterogeneous processing. So I think most talks happening in this room started with some thought of this sort, which is the fact that the compute demand has just been growing exponentially in the past 15 years, ever since the beginning of the sort of the first deep neural net model, all the way to the large language models today. On average, so someone plotted like a regression line on this, which is that the compute demand from mostly AI applications has been growing at 4 times per year, which is far exceeding the Moore's law, which is no longer holding, even far exceeding Huang's law, which is a new thing. I think Huang is saying that its GPU processing power is growing every twice every year, something like that. And this is also exponentially faster than that. So this is actually deriving from very simple math, which is that the need for distributed processing is pretty obvious. So if you think about, let's say, the compute it takes to train something like GPT-4, which, well, is no longer the state of the art, but it's pretty close to the state of the art. Large language models is something around 10 to the 25 flops. You divide that by the number of flops on a single processor. So at that time, it was H100. So H100 provides about 10 to the 15th flops of compute per second. You do the math, and then that gives you 317 years of training time. And then we will not live to see that finished. However, if you are able to amass, let's say, 10,000 of those H100 chips, and then that brings the performance per second to 10 to the 19th, and then this would give you 12 days. Well, in reality, it takes a little longer than that because of all the inefficiencies that we're about to solve. But this gives you something much more reasonable to work with. So to put it simply, that means that we need a large cluster to run these jobs now, and then this is essentially distributed processing. And this is also, we're going to see, more complicated than just simple, like embarrassingly parallel processing. The other side of the story is the need for heterogeneous processing. So I should explain what heterogeneity means. It basically means that so homogeneous would mean that everything runs on one kind of processor. So in the ever since I knew about computers, it's always been the CPU. So for example, the Intel CPUs, the x86 instruction set. But with deep learning and all of these new applications, because there's so much so compute intensive, people have built all sorts of accelerators. So the most famous being the NVIDIA GPUs. It's now the largest company in the world. AMD has something like that. There are specialized chips for like video decoding, not just even for machine learning. And then I think yesterday Amazon announced Trainium 2, which is which just proved that. And there's TPU from Google, which just proved that the kinds of accelerators, the kinds of processing units has become much more diverse. And then each of them has their unique sort of compute paradigm and the way you execute things on them. So that makes, compared to the world like 20 years ago, where most processing is done on CPU, this is a very different world. And we kind of have to reuse them because the accelerators are about on the order of 100 to 1,000 times faster as specialized workloads, such as machine learning, such as video decoding, video re-encoding, stuff like that. So that moves that 2 or 3 orders of magnitude of time can move the needle a lot. So to summarize, the trends observed is that one, more applications will require distributed processing. And second, more applications will require heterogeneous computing. So that's that we arrive at the topic today, which is how can we build efficient systems for distributed heterogeneous processing. So I'm going to argue that the most important thing here is extensibility. What extensibility means in a few aspects. Well, one, I think it means flexibility. So because we are now dealing with a variety of execution hardware, they have very different way of execution models. So for example, some of them you can run batch processing. Some of them require sort of a streaming processing mode. There are some in which a hybrid mode is better. So flexibility is very important. It's very important to be able to for a system to support a diverse range of execution patterns. The next is adaptability, because what's also getting more complex, in addition to the heterogeneous processing, is also that the data that we're processing, or in general the nature of the workload that we're running. So you have multimodal data, now you have images and videos, and then you can have much bigger variety in workloads. And furthermore, the sort of how the economy changes now is that these jobs run in very large clusters on the cloud, and cloud is elastic, as in that you can get more or less resources depending on both the supply and the demand, and then that also puts requirements on the execution system to be able to react and adapt to elastic resources. And finally, it's interoperability. So what this means is that I think modern jobs has become complex enough that it needs to go through usually multiple processing systems. For example, you do some sort of say ETL workload, and then you may need to do some stream processing or like concurrently some stream processing, and then you need to go through some machine learning framework. And the current state of the art is that you really have to go through multiple systems, which means, well, it's difficult to manage, it's difficult to orchestrate, it's inefficient because the boundaries between these systems usually means that you need to write them down to S3 or some persistent storage, which could be really slow, as we will see. So one requirement for an extensible system would be the ability to run these applications and then allow them to interoperate with each other on the same system. So the structure of this dissertation, yeah. So the sort of one theme of this work is that we want to build these systems or these execution frameworks on a common backend, and we choose Ray for that. I think people in this lab are very familiar with Ray. It came out of this lab about 6 years ago. Yeah, I think we'll get into the details, but Ray definitely offers the flexibility and the extensibility that we need to build such systems. It is in Python. It's Python native, so it's very, very easy to run machine learning workloads on them compared to previous generation systems. And I think it has the right level of abstraction, so it makes a lot of things easier to write, but also retains the flexibility and also provides the performance. So in this talk, we'll go over two libraries or frameworks that we build on top. One is Exoshuffle. So this is for running large-scale shuffle workloads, which we'll talk about what they are. And the other one is we call it the streaming batch model. And both of these are running in the Ray data library. And so the idea is that with these libraries providing enough flexibility for execution, now you can run all sorts of applications on top of these libraries. So that means that users want to write like a data processing pipeline can be easily doing that. They want to run machine learning or inference, batch inference, all sorts of things. RL can be doing on top of this library. Okay, so we'll talk about the first one, Exoshuffle. So this is an extensible shuffle architecture. Yeah, so let's see what shuffle means first of all. So shuffle here does not mean random shuffle in a mathematical context. It means so it is actually a key operation in distributed processing. It means that so think of a kind of a MapReduce style system where you have, let's say, the map stage where each partition is being processed, and then there's a reduce stage, so reduced by some key of some sort. And if you think about it carefully, then what happens in the middle is that every partition needs to send some part of its data to every other partition in the reduce stage. So this creates an all-to-all communication pattern, which we call shuffle. And you can think I think this is the most expensive communication pattern in distributed data processing, because this is literally every node needs to send data to every other node. And shuffle actually is the backbone for many other operations that you can build on top. So you can think, for example, in data processing frameworks like Presto, in Spark, and the older days in Hadoop. Lots of these SQL operations actually involve some version of shuffle. So every time you need to join two tables, or even in one table, you need to group by some key, you need to do a global sorting, you need to even select distinct elements. This all involves shuffle in the background. So some quotes from the papers on shuffle. LinkedIn reported in 2020 that petabytes of data is being shuffled every day on their Spark clusters. Facebook said, Meta now, like tens of petabytes of newly generated data every day, and over half of their Spark jobs involves at least one shuffle operation. So this makes it really a very difficult problem to solve, especially at scale. So let's think about that for a little bit. So what is challenging about shuffle, right? So the biggest thing is that it's an n-squared operation, and in the number of partitions. So this gets into big numbers very quickly. So if you think about it, you have some math here. So if you have, say, a terabyte of data, you have 10,000 partitions, such that each partition is 0.1 gigabyte, which is pretty common. This is not a huge number, but then if you need to do a full shuffle, this results in 100 million of shuffle blocks, each only 10 kilobyte each. And then this makes it difficult to optimize, because this means that each of these 10 kilobyte blocks need to go through disk I/O, network I/O, and into memory boundaries. The efficiency of I/O for these smaller blocks is really bad. Fault tolerance is really challenging, because now you have 100 million transfers. And they can fail at different stages of the operation, and then you want the system to be able to handle that. Load balancing is difficult because, well, in a perfect world, everything is uniformly distributed. But now you have, in real world, you have hotspots, and then this makes balancing the loads really difficult. And if you don't balance the loads, then you will get really bad stragglers that slows down the entire operation. So the traditional sort of solution to this is that people recognize this is an important problem, so they go off and build a dedicated system for supporting shuffle, namely just for supporting the transfer of these shuffle blocks. There are a lot of such systems built, some of them in the literature, some of them from the industry, but the TLDR is that it's really costly to develop and maintain, because now they usually run alongside, say, Spark. So you need to maintain a separate service that you need to allocate resources for them. And a lot of times the actual solution to like these smaller blocks is usually some version of merging them at some part of the execution. Depending on the hardware, the actual best strategy differs, but it's really not that different from each other. But because you're building these as sort of monolithic systems, if you have different strategies, you need to build them as separate systems. You need to sort of rebuild a lot of the same data plane stuff, but just in order to support a different algorithm. And then you have your data processing framework running as the customer to these systems. So two problems here. One is that the control, we call it the control plane, the data plane are tightly coupled in the sense that the moving of the blocks is really an independent problem of how and where or when you want to move these blocks. So we call the decision to figure out where to merge blocks and stuff, the control plane, and the actual implementation, the data plane. The data plane actually does the same thing, even in different systems, but because they're tightly coupled, you need to sort of rebuild them as you build a new system. The second sort of inflexibility is at the boundary layer. So the shuffle services provided to Spark is has a very specific semantic, which is that it's responsible for shuffling the blocks. This is fine for data processing applications, but as we can see later, for say machine learning applications, they want the results, for example, in a streaming fashion. This makes it sort of impossible to express the semantic in this design. For example, you can think that in like machine learning training, you have a bunch of training data sitting, and then before you want to send them to your neural network for training, it's desirable if you can do random shuffle for the training data on the fly, because that gives you much better that like decorrelates the training data. It prevents overfitting, all the good stuff. But it's a really difficult thing because Shuffle, as it's currently built, like these Shuffle services are not able to be just easily plugged in to these frameworks. So to solve this, our solution is Exoshuffle. So Exoshuffle, in the sense that we build Shuffle at the library level rather than at the system level. And what that allows us is to have a common data plane. Again, we use Ray for this. And then there's this level of distributed futures API, which we'll talk about, which enables us to easily write Shuffle. And also in this way, separate out the data plane from the control plane. And now you have different Shuffle optimization strategies that you can implement at the library level. And then finally, your general applications, data processing, ML, training and stuff can run on top of this architecture. So what we achieve here is that one, you decouple the control plane from the data plane such that you get much better interoperability between shuffle and applications. So on the control plane, this is now easy to implement shuffle algorithms, and it's flexible to interoperate with other applications. On the data plane, we show that through this work, it is actually possible to provide good performance and scalability with as competitive with monolithic shuffle systems. And the sort of key to do that here is that with this distributed futures abstraction, which I think turns out to be a very good design of Ray. So let's look a little bit of code. So it's actually surprisingly easy to write shuffle naively in using this API. So I assume people are familiar with Python, but these new things here, so I explain. So Ray basically provides a functionality to run functions as remote tasks. And the way to do that is that you pass in this .remote calls, such that you have a map function, and now you call it map.remote, and you give it an argument. And what this call returns, so it returns immediately. It gives you like a future handle of the result of this operation. But this line, the first line, returns immediately, and then now you can use this map out argument, which is a list of handles pointing to objects in the future and also maybe on a remote node. This is why we call it distributed futures. And we're able to just pass them to the reduce task. So now basically in these two lines of code, you create this all-to-all communication pattern. So you declare that, and then this is essentially shuffle. Yeah, as we said, the return values can be passed around these tasks. Yeah, and then I won't go into details today, but it turns out that it doesn't need a lot of lines of code to implement something more complex. So these sort of shuffle optimizations we talk about in the literature essentially boils down to some sort of merging of blocks, either before you do the network transfer or after you do the network transfer, and then yeah, you can look at the Exoshuffle paper, but it's not a lot of lines of code to implement either of these patterns. So I think the key thing here is that with Ray, it's much easier to write such applications. So the application specifies the task graph, or the two lines of code that we had to specify data dependencies. Ray allows you to specify when the task starts and then where to run these tasks. And then everything else, the system sort of like a generic data plane layer provides it for free. So that includes resource allocation, memory management. So fully managed memory, that means that transfer of objects is implemented sort of independently of the shuffle strategy. Spilling to disk and then restoring from disk. So this gives you kind of a memory hierarchy from node memory to disk to even external persistent storage. And the garbage collection through reference counting so that you don't leak memory. Pipeline I/O is important because you would want to overlap, say, network transfer with disk transfer with the actual computation. Ray provides facilities to do that, transparent facilities to do that. And then finally, fault tolerance. So Ray would be able to recover failures through something called lineage reconstruction. So essentially tracking how an object is created and then being able to recompute that during fault recovery. So let me quickly show some experimental results. First, it is just much easier to write different shuffle algorithms. So here we compare a few shuffle algorithms, their sort of system implementation versus the Exoshuffle implementation. So it is an order of magnitude less amount of code to write. And the reason we can do that is because the common stuff is being factored out, in the Ray system, so that just the difference in these shuffle algorithms doesn't end up in a lot of changes. And secondly, the performance and scalability, we ran some experiments, is really there. We compared with, so Spark has a push-based shuffle service. As it turns out, we can basically be competitive on at the scale of like 100 terabyte of shuffle. Maybe the more interesting result here is that we actually ran the Exoshuffle system on the CloudSort benchmark. So this was this was all the way from Jim Gray's time. This is about what is the most sort of cost efficient way to do sorting, and why we choose sorting is because it's not a difficult thing to think about, but actually it's a very challenging thing to the system because this means that well, this is essentially testing the raw shuffle performance. So the previous record was set by Apache Spark in 2016. And yeah, when we ran this, we're able to get even better results. So even less than $1 per terabyte. We ran this on AWS with Exoshuffle. I should add the caveat that there is some of this better result is because the hardware got cheaper. So we actually ran this math. So if we took the results from 2016 and then we see how much it would cost in like today's hardware, it would be a lot cheaper. It would be like 1.15, but still the rest of the 15% is because we're able to run shuffle more efficiently and then even also with like a much less implementation effort. Yeah, I'll show one more result here. So this is, we actually use Exoshuffle's shuffle library and then hook it up with a machine learning training workload. So this is training, I think, a tabular classification model on a tabular data. So it's especially beneficial if you can do a full shuffle of the data before each training run. And as we can see here, once we plug in Exoshuffle, the rate to convergence got better, and then we also got to better accuracy. So the takeaway of Exoshuffle is that we show that an extensible architecture can reach the performance and scalability of monolithic systems, and by decoupling control and data planes, Exoshuffle can benefit a variety of applications by providing efficient shuffle. So we have integrated this into Ray in the form of the Ray data library. It's working with a wider variety of machine learning training libraries. And also we have some experiments running this with data fusion to provide some sort of a distributed SQL execution engine. Okay, so let's...
Yeah, can I ask a question?
Oh, yes.
So how complicated do you think it is to like automatically generate the shuffle algorithm? Because the shuffle algorithm must be implemented to improve performance. Like why this step is currently manual? Because they're on the top level, it is the same semantic.
Yes.
Right. Why not solving it through like a compiler type of approach? Yeah.
Okay, I think that's a great question, and I think that could be the next paper. So yeah, so you're right. We did a lot of sort of. I think to answer that question, you need to think about the design space and then see if we can just sort of automatically search it out. I think it's definitely possible, and I think Exoshuffle definitely offers a way to do this, because. Yeah, so at the end of the day, it comes down to the decision of how big your shuffle blocks need to be, and and where at what point of the stage it's better to do the transfer, and how do you do the pipelining. I think the design space can be sort of described in like a lower dimensional layer rather than just like the space of all possible execution schedules, and then. Yeah, and then with that, I think it's definitely possible and then the decision is based on the actual hardware characteristics, right? So for example, hard disks are slow to seek, so you need like longer IO, like you need bigger chunks for IO reasons. SSD is not so much sensitive, and then depending on your network layout, the network transfer could be fast or slow and stuff, and your failure rate and stuff like that. So I think you can definitely like write down these factors and then sort of design a reasonable search space and then do the search. I think that like this auto tuning of shuffle is definitely something interesting.
Yeah, thanks. Yeah, I think because you have reduced the line of code, so maybe your work can make this possible.
Yeah. I mean, I will see for the next paper as well. Like auto scaling and auto tuning has always been the goal here. And it's a difficult question to design it such that it's feasible but also useful. But yeah, we'll see that I guess in the next work as well.
Thanks.
Yeah, right. So one problem that we mentioned in Exoshuffle is that it turns out that machine learning workloads a lot of them require streaming consumption of data. So this actually makes this inspired us to build the streaming batch model, and then let's see what the sort of the problems are. So this is mostly for dealing with modern machine learning models because they can not only be, the early days machine learning models are classification models, they're discriminative. Now they're also generative, as in that the input and output of these models can be like images, video data, and even like outputs of other models and stuff like that. And then this just makes the pre and post processing steps of the machine learning workload non-trivial. So let's think of like a video processing pipeline. So you have all sorts of models that can now generate videos, they can make super resolution, they can deblur, denoise, style transfer, do frame interpolation, all sorts of things. And if you think about how this pipeline looks like, it's actually not just like throwing the video at the GPU, but rather there are the video files, which is very highly compressed. You need to decode them into lots of frames. You need to send the actual raw tensor data into the GPU to do the inference. And then the GPU spits out some tensor, which you need to encode back and upload to your persistent storage. So the difficulties here are that one, so this also involves heterogeneous processing because you're going through different kinds of processors. First is that different resource requirements and physical parallelisms of these different executors. For example, you have one GPU that expects just a stream of chunks into it, and on the CPU, on the other hand, it's a threaded model. So, and then you have like a lot more CPU cores versus the GPU unit of execution. Second is the large intermediate data size. So example, like even 1 minute, so like 1 minute of video like is 5 megabytes. But then if you count the number of frames, you can have like thousands of frames, and then you can end up the decoded video. Actually, the tensor could be as big as 10 gigabytes. So what this means is that the intermediate data between these stages, because traditional like say batch processing system think in stages, the data in between these stages is so big that it can only be like streamed through the memory. It's impossible to like spill this much of data to disk, and then it also doesn't make any sense to do so without compression. So this also affects the design of the execution pattern. And third is just workload variability. So let's take video for example. Some videos are more compressed than others, and they take longer or shorter to decode. Downloading and this non-trivial amount of data takes a variable time of download. So that essentially means that these operators here have different have different execution times, and then that will make resource allocation difficult. So let's think about how you would naively run this in parallel. So the naive way is that we just run each like in the threaded model. So each of these threads is one a unit of execution. So you run like the first stage on CPU, like this. So you have the first stage on the CPU, the second stage on the GPU, and then the third way on the CPU. And then you can run as many threads as you have GPUs. Except the problem is that, so you run this in sort of a serial pattern. The problem is that now you have this lots of more CPUs idling because you cannot, in this model, you cannot run more threads than you have for your lowest physical parallelism. And then, as you can see, there are also bubbles in the schedule because now you're sort of wasting the actual CPU compute that you can otherwise get. So this is not good for sure. The one way of solving this is the sort of the BSP model. So this is employed by the batch processing systems. So the way you do this is that you run everything on the first stage, at maximum parallelism on that piece of hardware, and then you run the second stage on that hardware, and then you run the third stage. So yeah, so this would work, except for the fact that now we have in between these stages, there are synchronization barriers, which is expected. But the problem is that there's also a huge amount of data here. So like, you can easily generate like terabytes of data in between these boundaries. And then if you don't have that much memory, you have to spill them to disk, and then that would be just prohibitively slow. So so another class of system is stream processing systems. So these systems basically run well, they process incoming streams, and then they can basically set up operators, and then you can have data flowing through them. So the downside is that you have to sort of decide how many operators how much parallelism you want for each of these operators. So I say I reserve 2 CPUs for the first operator, and then 2 for the third operator, and then the GPU runs on the GPU. So this will give you something like this. So it's better as in that you can now overlap execution, and you can change the operations. The downside is that it's not the most efficient thing if these tasks have different lengths to run, like have different execution times, because now it's still not the most optimal thing. And then the reason for that is that you are pre-allocating resources instead of doing them on the fly. So what we actually want, if you try to squeeze this timeline, is something we call the so again, static resource allocation leading to underutilization. What you really want is something we call the streaming batch model, which is that you can allocate resources on the fly. So you can say in the beginning, there's no dependencies, so you allocate as much resources as possible on the first operator. And then as things are going, you can start scheduling the post-processing steps on some of the same CPUs because they are done during the first stage. And then by this means you get a much tighter schedule, and this is also responsive to any workload changes. So the key idea here is that we call it essentially just-in-time resource allocation at the task granularity. So we have a central controller that allocates execution resources per task instead of ahead of time pinning execution slots to different stages of the operation. And then we also can allocate memory based on the actual task output size. So this enables us to do things like dynamic repartitioning pretty easily because now we can make these sort of decisions as we go. And then the central scheduler is aware of the global memory usage, so we know how much buffer we have in the memory that we wouldn't overschedule tasks. Yeah. So one of the biggest workload that we run on this model is the Stable Diffusion pre-training. So here we actually used Ray data. So this is implemented in the Ray data framework. The Stable Diffusion pre-training, one sort of epoch uses about 1 billion images, and then it's kind of a complicated pipeline. But the high level thing is that you have an image and you have a prompt, and then the image needs to be encoded using some like autoencoder, and then that needs to run on the GPU, and then the text needs to go through a text encoder, and then and then both of these embeddings now go into a trainable model. So so you can see this requires different hardware and even different size GPUs because it's much faster to use like a smaller GPU for this autoencoder. And then so this results in this sort of execution pattern. So we have the big GPUs, say A100, H100 for training. You have the smaller encoders GPUs that are more efficient doing the encoding, and then you also need a lot of CPUs on the side to like do the data, the decoding, and all of those steps. So our results show that so we compared a few different versions, and if we map these back to the execution patterns, the PyTorch streaming version is essentially the sort of the naive parallel version in that so PyTorch just runs those data loaders in their processes. So essentially you're doing these serially. You can parallelism across the GPU, but that's as much parallelism as you get. The Ray data, the implementation, we have 2 versions. One is sort of an offline version. We call it staged in that we sort of pre-compute embeddings. And I think this is actually what a lot of people in industries do still today. You pre-compute the embeddings, and then you directly train from like load data from the embeddings for your training. And then the ideal world, you would do this sort of everything online. So this is the streaming batch version. The takeaway here is that the total running time for streaming batch is a lot better than not doing so. The cost is a little more subtle in that because on the cloud you can actually in the staged version. Here is the waste of resource, but on the cloud you can actually just turn off these GPUs on the other stages, so you actually can save a little bit of money. But and there are other efficiency reasons. but we think that this essentially enables online processing as a possible way of executing these sort of large-scale distributed heterogeneous patterns. So that concludes the streaming batch. Yeah, and then as I alluded to earlier, auto-scaling the streaming batch processing is definitely something that we want. Well, so in the ideal world, right? So now we have these sort of complicated workloads. The ideal case would be that the user just states the stages of computation and maybe some hints on how much each of these stages need, and then the system would figure out the best hardware resources. You will automatically decide to add or remove resources, and then it will automatically reconfigure during the execution. So something like this, right? So initially we know we need GPU, we need trainer GPUs to train the Stable Diffusion model. So we will allocate that, and as the execution starts up, it will figure out that it needs these additional supporting nodes to run the pre-processing steps, and then maybe you need additional CPU nodes just for running just for doing the post-processing or something like that. And then this sort of can dynamically adapt as the training job goes. So I think this is essentially one of the vision of the sky computing. And then now I think with the streaming batch model, because the execution model now is much more adaptive to these changes, this is actually a feasible thing to do. So we arrive at the conclusion slide. And then here, I think the conclusion is that we show an extensible architecture is viable for building the next generation heterogeneous data processing applications. So we have seen a few benefits of this. It's easy to develop. Given that you have such a system already, it's easy to develop new algorithms on top of it. It's flexible to all sorts of different application semantics. So we see how data processing works. We see how streaming execution works, and then it's adaptive to workload variability and to resource elasticity. It is interoperable between applications. We see how the machine learning applications can now benefit from shuffle optimizations that were previously only available in dedicated data processing systems, and the underlying system can have the performance, scalability, and fault tolerance built once, and then benefit a large variety of applications.
Sorry.
Can I mute? You get it? So maybe.
All right, cool.
So that concludes the technical part. I think I can take some questions here before we go to acknowledgements, if anyone here or online want to ask.
Yeah. Actually, why don't you go to the acknowledgements and then we can come to the questions?
Okay.
It will be simpler this way.
That makes
sense.
Yeah. Okay. I think that's right about enough time. Yeah. Okay. So acknowledgements. So yeah, thank you everyone for staying until now. Yeah, I'll begin by saying something about Jan. So Jan is my advisor. I've been working with him since I think late 2019. We went through COVID and all of that. We're still going through that. But I think I want to say a few things in response to what Jan said about my journey in the beginning. So I think maybe the most important thing I learned from Jan and from this lab is that the most important question is what problem you're working on. I think Jan said this to probably every new student in this lab, which is that you can solve problems, but the more important question is what you decide to work on. So I think the beginning slides about distributed processing, about heterogeneous processing has been sort of the vision for quite some years, and I think the fact that it's still relevant means that that's probably the right call. And I think I'm very glad that I was able to work on that. And then maybe another thing is that I think Jan has this philosophy of you find a problem, then you try to get like a end-to-end sort of working MVP soon. And the argument for that is that because if a problem is easy, then you solved it, and then it's useful. So you made something useful. And then if it turns out to be more complicated than it is, then now you have a real research problem to work on. So I think that has been a good approach. Yeah, I'm very grateful for Jan. Throughout the 5 years, there are. I think he's patient enough that when I'm sort of wandering around things, he kind of believed in me that I can sort of make something work. And then I think he told me to finish, like just finish what you started, which I think is a very good advice too. And that sort of led me here today. I want to thank my dissertation committee. So Joey is here. Thank you for coming here. Daniel is here. I think so. You guys helped me a lot with the qualification exam to sort of shape out this dissertation. Yeah, thank you for all the comments and all the help. Yeah, and then thank you for providing feedback to my thesis, or will provide feedback to my thesis. My sort of unofficial advisor is Stephanie. Well, so Stephanie was still a PhD student in the lab here. She's not an assistant professor at UW. I think in reality, I spent probably the most time with Stephanie throughout essentially pretty much all of my research projects here. I think she has been very patient in sort of making me a better researcher. She writes really, really well. There are times that I think there's no way we could submit a paper, but she's somehow able to. And these sort of stories, as you can see, are like the motivations of a paper of a work is sometimes difficult to articulate. And I think she was very good in showing me how that's possible. So someone in this lab once asked me for advice to choose between UW and Berkeley this lab. It was a very hard question to answer because of, I think, support that I get from staff. I want to thank all of my collaborators. So some of them are here today. I'm very grateful that you guys can come out here at 9 a.m. So yeah, so everyone here, it's me, Isaac, Kenneth, and Gautam, and then the rest of people who I have a paper with, and a lot of more people that I wish I had a paper with. I want to thank. Actually, we worked, in addition to people in this lab, we worked with a lot of people at any scale. So that was a rate core team, and then there also the rate data team. I think none of these work would have been possible if they hadn't built such a good system. The lab staff, so Bolden, Ivan, John, Kaylee, Kat, and Trem, they have been very supportive throughout my time at the lab, and also the departmental staff, who I think some of them are gone now, but Jean, Shirley, Carissa, helped me navigate through all the paperwork through the Berkeley system. Yeah, and just everyone here on the call here, everyone I met at Berkeley. I think so. Also, I think one really important thing here is that I'm highly opinionated, but I think people is the most important factor, to the success of any part of your career. I think the people I met here and work with at Berkeley are really the most supportive and helpful and just cheerful people I work with. I think, and I think that's really what got me through my PhD journey. I particularly want to also thank, I'm not sure if they're on this call or not, but people who sort of got me started into research. So this is about, before I started at Berkeley, I spent 2.5 years at Facebook doing sort of machine learning research. So Satish was my first manager, Eric was my director, and then Kaushik I actually worked with and also helped me into Berkeley. Yeah, so before that, I was just an undergrad. I did not know what CS research was. I think they showed me what it is and how it can be interesting and how it can be meaningful. So I'm very thankful for them for essentially guiding me into research in the first place. Yeah, I want to thank my girlfriend Sifei, who I met last year, and I had a lot of good time with, and then actually moved to Boston for. My parents who raised me, I grew up in Beijing until I was 18. I think without them, there's no way I'm here today. And then they convinced me to start and to finish my PhD, which I'm very, very grateful for. So I will end here, and then any questions, comments, I think now is the time to take them. But thank you very much.
Okay, so we have time maybe for one question or two. Any question from the audience? So Frank, this is one question then. If you were to have you work for, if you have more, say 3 more months or 6 more months to work for your PhD, what would you do?
Yes, that's a great question. I think as I mentioned in the sort of the last part of each of the sections, I think there are definitely interesting things to do.
Yeah, I know, but which one would you pick to do it? That's a question.
It's for another grad student.
Okay. That's what you all say, but yeah, no, I think the array data work. So I think the some version of auto scaling on that is definitely like feasible within a 6 months time. I think just essentially gets us one step closer to the sky vision, which I think is still a great vision. So essentially extending that work to be able to make some decision about resource allocation, being able to scale up and down, and then yeah, I think that'll be also very relevant to the current sort of what people do in industry.
Okay.
I got one question. So if everyone's buying these really fast interconnect clusters with specialized network hardware, how does that affect what you're doing here? Like I bought this really expensive NVIDIA cluster. Should I use this still? Or what would you change? Or did you address that condition?
Okay, so first of all, I did not run any experiments on them because I don't have them. But I understand the question. I think it's still like at like a very, very high level. Then if you have like a really big box of H100, that essentially is, I don't know, one. I think like
I got a whole data center full of H100s. I'm like, okay.
That's okay. Yeah, that's still a problem. And then yeah, I kind of know that's still a problem in the sense that I think the like these problems in like heterogeneous compute still exist. I think that changes something about your assumptions of say a network is slow or like for example, I think something real like the connectivity to S3 is still a very big problem. And then there's no way that you put these H100s in the S3 clusters, as far as I know.
Well, I'm saying I have a cluster of InfiniBand, ignore the GPUs,
right?
And I have a ton of data on these InfiniBand machines. How would your work live in that cluster? To use InfiniBand, how does it change the dynamic?
Oh, I see. I think okay. So I guess one part of the problem is the engineering problem, which is that you definitely want to use InfiniBands.
Yeah.
And I see. I'm not super familiar with that, but my feeling is that you can also abstract that. Just like ideally, the user doesn't need to worry about like the interconnect. And I think the challenges with say disaggregated compute and storage is still real. I'm pretty sure that I don't think that all of the data can just exist on your like supercomputer. I think it's still so the question about like say memory hierarchy, storage hierarchy are still real problems.
All right. Should we
Let's thanks again, Frank, and congratulations again, Frank. And all the best of luck forward.
Thank you so much. I'm happy to talk more offline about anything I discussed.
Yeah.
But yeah, we'll call it a day here today.
Congrats.
Congrats. Okay.
Congrats, Frank.
You guys aren't seeing this at any scale? People buying